to get the stuff will be environmental.
Okay, guys, let's do this. Then with that. Oh well, then I'll make it worth your while. Let's do it. Otherwise, we have to come back. I don't want to come back.
What his first never does anything. Anything. Oh, what? I'm nuts. I'm nuts.
Let's skip on that page. Right, let's go to page 29, please. Okay.
Use everyone.
I don't know exactly what you want. Right, okay, so on page 29, okay. This is kind of a summary of if we divide things into quadrants. On the predator-prey model, sometimes they're going to ask you for the domain and range where things happen. Okay, so as you can see over here, in this quadrant over here, both are increasing in that green region over here. Okay, in this region over here, remember it's always going in this spiraling towards the center, right? They both are decreasing. Okay, et cetera, right? So on this page over here, yeah, predator increases, prey decreases. Yeah, predator is decreasing, prey increases. Okay, remember, we're always moving anti-clockwise direction towards the center of it. Okay, so that's your oscillating plot. So they talk about oscillating plot. That's what you're looking at. What do you have to be able to identify? The initial points. Well, not really furthest to the left. I don't really like that so much. Furthest away, I think, is a better description. The position of equilibrium, which generally clusters around a central point over here. Characteristics. They often, right, sorry, I'm speaking cut. Previous, so this is your phase plotting over here. Go back to the previous page, sorry. Right, on the previous page, plots, blah, 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 present are generally used to a spiral plot. Further, this is an important idea, please highlight that. Remember, these are each, it shouldn't be a continuous curve. Okay, the further apart the points are, the more dramatically the predator and prey populations are changing. So in this thing over here, your path goes from here. This is your general path, the diagram here. Okay, there's your population. But remember, it's not all of these models are discrete models. Okay, so all of these models are discrete models. So here, in this region over here, in red, the populations are changing dramatically. Okay, and over here, as the dots get closer towards each other, then they're not changing as much. I'm actually going to kick people out because, quite honestly, you know what? All right. So, examine the phase plots above and hence determine. Let's just do this quickly. The initial number of predators and prey. So which is your starting point here, guys? That point over there, right? So prey equals 200 and predator it's like about 5, something like that. Okay.
You
with me? Right, go write down the number where predators and prey reach equilibrium.
So what would be the leniency of reading off this graph? Like 2 points, 1 point?
We'll do that next as another question.
Okay.
Okay, right, so. All right, what did you get for equilibrium? Equilibrium is looking at about somewhere down here. So for prey, but where? And for predator, it's an unusual equilibrium. Okay. Prey is equal to about 53, 55, something around about there. And predator, I said 83. But they're not exact sciences. Okay. Right, so this is your spiral plot. Okay, so there are two ways to represent spiral plot or phase plotting. Okay, that's the one way we can represent it. We'll look over that. We'll worry about the domain and range later. Okay, and this code on there, but then we get this oscillating plot, which is showing the same thing in a different axis. Instead of now, okay, in the previous axes, what your axes were predator and prey, right? Now we have time and two different graphs for each thing. So these are diagrams of the same situation. And this one over here, this representation over here. Okay, so what does it say? It started off with those things and started off at the prey of 200, predator at 5, and settled at prey at 55, predator at 83. Okay, and that's when you're comparing when you have predator and you have prey on the same set of axes. Okay, if I have, now you've got time on the x-axis. Okay. Right, and you've got population of each one. So prey is included. And on the previous diagram, the starting point, we had in blue the prey started at 200. Okay, and the predator started at 5. Those are those 2 points over there, right? Okay. Then there are these massive oscillations. What do the massive oscillations in the beginning look like on the other diagram? So here you can see it actually oscillates. Okay, but just have a look here for a second. Those comparative time periods to the left of that, that initial time is where in this diagram. Okay, in the other diagram, it's this beginning part over here. Okay, in yellow, right? Where things are fluctuating. Sorry, now it's in red. Where things are fluctuating a lot. Okay, population. How do we notice that? The gaps between the dots are really, really large. Okay, but in this diagram, perhaps more apparent how those populations are oscillating. Okay, it's showing the same thing. Okay, on this one, you can see pretty obviously that the red, which is the predator, settles at around about 83, and here the prey settles around at about 50, whatever it was, 55, I think we said. Yeah. Yeah, oscillating just shows the actual numbers against time. Okay, so the axes have changed. Now it's time against population. Whereas in the previous one you're comparing, on the x-axis you had prey and you had predator, you're showing the relationship between the two things. Okay. And normally these waves are in some kind of a sync. Okay. Normally the crests follow each other as the numbers increase and decrease. So to read off the initial numbers here, you just go to the y-axis. Okay. And you get predator is equal to what? Predator, the initial number of predators was 5, and the initial number of preys was 200. And equilibrium, predator was 83, prey was. Okay, you see how those two, are you okay with how those two diagrams related? Okay. Can I move on?
Yeah, we can say
200. All right. Okay. All right, let's answer this question. Off you go. Okay. First thing I would do is this. Okay. It's not a bad idea, especially because you get these questions over here about domain and range. Okay. In that situation, you kind of figure out where are quadrants. Quadrants always the origin of the quadrants is always at the equilibrium point. That's equilibrium point is how I think of the origins of the quadrants, right? Yeah, because then in this top right quadrant, what's happening over here in all of these regions? So there. The same thing's happening in that region, right? Yeah, what's happening over here? Foxes are increasing. And rabbits are decreasing. Do you agree? Foxes, it's going up. Remember, it's always going in that direction, right? So foxes are going up, but rabbits are going down. Okay, see how in the quadrant the same behavior is happening. In this quadrant over here, okay, if we're going down like this, what's happening there? In that red region. Foxes' numbers are? Okay, foxes are decreasing and rabbits? Rabbits are also decreasing. Not as much. Yeah, it's like, okay. In this region over here in yellow, what's happening there? Nothing to the rabbits. Rabbits are starting to increase, but foxes are still decreasing, right? And in this region over here, last one, black, both increasing, right? Foxes are increasing and rabbits are increasing. Yes? Yeah. Right, so to answer those questions. Which one? Part of the main range. No, it's sitting there for now. Yeah, we can do that on the next one. Yeah.
Sorry, so I needed to help Lexi with something. She wasn't feeling well, but just has a
That's all right. It's fine. Okay. So initial number of foxes and rabbits, guys. What did you get for that? Okay. Foxes. I said foxes were 10. Rabbits. The foxes was equal to the initial number. So we're looking at, sorry, the initial point is over here, guys. That's your initial point over there. Okay, so 300 foxes is equal to 10 and rabbits is equal to 300. Are we happy with that? Okay, off we go. Try B and C. C, I'll help you with that. Okay. Like, what do we get at equilibrium? Foxes 28. So I said the same thing. Okay, and you did obviously leeway. Foxes look like 28. Rabbits look like about 40 something. I said 48. You good with that? Right. Everyone happy up to there? And the next question says, the domain and range, rabbits are increasing and foxes are decreasing. So it's that yellow region over there. Okay, so where does that happen between this yellow region? Okay, what are the X values? Okay, where this yellow region happens. So for C1, X is absolute equilibrium, right? Okay, which was at 48, eh? So X is an element of 0, 48. Those are your domain values of the yellow region. All right, then the range values. So always use your equilibrium as a one boundary usually. Well, usually. So what's the range of the yellow region? Yeah. Doesn't matter. Okay. I didn't include them, but it doesn't really matter. Okay. That's your domain and your range. The smallest Y value in the yellow region. No. No, your Y value, guys. We're looking at Y values of the yellow region. It looks like about 8. Yes? And goes up to this equilibrium point, which was at 28, eh?
Zero.
You look at different scales. Rabbits is on this axis. So I'm looking at, for this one over here, the domain values are from here to here.
Yes.
So the domain values are from 0 to 48. That's the rabbits. Okay. Foxes is a range.
Two.
Okay. Foxes lies between 8 and 20. Okay, you with me? All right, try the next one. We are the foxes increasing and the rabbits are decreasing. Which color in my diagram? Where the foxes are increasing and the rabbits, which quadrant? The green color, yeah, top right quadrant, right? So basically, I'm looking for the domain values of the green things and the range values. Now, this is a bit sneaky because actually they kind of increase. I don't really, personally, I've never really put these questions. I don't really like these questions particularly, but you could really say the starting point is pretty much there where they're increasing.
Yeah.
So I'd say it's increasing actually from 0 till about 300, from 48 till I said 48 till 305. And slightly out the quadrant. 5. Okay, so this will actually be my starting point, and then go right down the range. I said, what did you guys say? I said from 20, I used this as my starting point. Okay, so I said y is an element, and the approximations of 20. I said up to the top y value of, said about 63, something like about there. Okay. The y value there was about 20, roughly 20. No, there 63. That was the region one. Okay, I'm not particularly fond of those questions. Okay. Now, once again, guys, this diagram here, have a look, where the axes are rabbits and boxes. And that is in your spiral plot. What's the other word that you put spiral? Phase plotting. Okay, this is called the spiral plot or a phase plot. Okay, in this one over here, this is your oscillating curve, right? This is an oscillating plot representing that same scenario, right? So, except here, the rabbits are in blue. Okay, and time is on the x-axis. Okay, so what's happening? We're getting that wild fluctuation, and then they reach some kind of equilibrium. Your answer should coincide. Check it. So initial numbers are going to be on the left axis. The foxes are in red. So the initial number of foxes looks about 10, and rabbits is over here. That's your initial number of rabbits over here, which is, well, that's the same as the last question. Okay, foxes 10, rabbits 300. That was this point over here, right? Foxes 10, rabbits 300 was over there. Was your starting point. On this graph, foxes is done over here. This red thing over here, there's a foxes population of 10. Okay, that's initial fox population. This is the initial rabbit population. And they oscillate all over the place. Okay, so when does equilibrium happen for each one? Foxes are in, the rabbits in blue, it looks like what? Is that about 40 something? I'd say about 48. That about 48, that's where equilibrium's at the end over here. 48 about. Okay. What did you guys get for foxes? 28, 27, somewhere around about there. Easier. Okay. Okay. All right. Okay. All right. Okay, are you guys dead? Let's just push on. Okay. One past paper question and a 2-minute break. Okay. So I want to go though to this, come back to this one. Let's just do question 5 first. Okay, predator prey question. So this is the one from IB 2020. Okay. Right, give it a go. So a stoat is like this little weasel thing. That's your predator. Lemming is like a little fat mole. And that is your prey. Okay. First thing I would do probably is write down, okay, go to your formula sheets. Okay. And write down each particular model. Anyone on a formula sheet? Formula sheet down. Right, anyone else? Okay, right. So I always just write my, once they give me a formula, I write down the formula as it is on the formula sheet. So the prey are the lemmings. Okay. In other words, like the rabbit. Okay. And rabbit n plus 1 is equal to the rabbit plus a, which is the birth rate, r to the n, 1 minus r n over k, minus b r to the n fn. So that goes with this thing over here. So a lot of this is going to be about matching patterns, right? And this formula over here is for my prey, which is the foxes, and fox n plus 1 is equal to the foxes plus b rn fn minus c fn. So often it's just about matching those two things up. Right, first question. Are you killing me? Yeah, it's fine. At least it's on this board. Okay, try to answer those questions.
Crying in a bucket. Yeah, it's better than swearing.
Stop crying out loud.
No, you said crying in a bucket. So when we say crying in a bucket, but anyway, that works. It's what my mum used to say before she started swearing. When she was still polite. Your mother's worried about me next year. She I was still pretty nice.
Come, guys, try it. So guys, where does lifespan come in? Okay,
That's an A.
so C, what is C in this formula? Okay, C is equal to what? 1 over the lifespan. Okay, C, in other words, is the what? What did we say C was equal to? The death rate, isn't it? What's C equal to? I'm going to now. Yeah, C is the death rate, right? Okay, and so C, so for question 5.1, C is equal to 1 over life expectancy, right? Or average lifespan, right? So now I go to the formula. And what's C equal to in this formula? What's the number over here? The coefficient there? It's 0.1, right? Okay. So C is equal to 0.1. So 0.1 is equal to 1 over life expectancy. So life expectancy is equal to 1 divided by 0.1, which is 10. So if you can answer 10 units. Right? You, in this case, let's see. You want to read the question. So good question. So in the article that says the lemming is the main prey of the stoat, predator-prey model has been used to model the interaction between these two species. The period between iterations is 1 year. That's what it's telling me. Okay. And there's the various models. Okay, try 5.2 and 5.3. Okay. They call it intrinsic. Okay. Okay, so the intrinsic growth rate is this A over here. Okay. I prefer, so you can either think of it as intrinsic growth rate, okay, or the birth rates. Okay, it's the same kind of thing in this model, which is a bit confusing. Okay, so there A is equal to 0.8. Which is it's a percentage, it's a ratio, 80%. Okay.
I see, because it's, okay.
Yeah.
Sorry.
Okay, no, it's fine. All right, next one. What is the carrying capacity of lemmings on the island? Again, it's matching up formulas. Carrying capacity is K, right? So it's a question of matching up your formulas. Well, here is a K. Okay, that's got to do with the prey. So what's K going to be equal to?
That's enough.
10,000, right? So 5.3. Yeah, this is 5.2, 5.3. K is equal to the carrying capacity, which is
Populate the sum of the populations.
10,000 is the maximum amount of
Lemmings.
lemming. No, just lemmings. And that's for prey. That's the carrying capacity of the lemmings. Okay. Because that's got to do with this population. This is that model over there, right? Okay. Are we good? Okay. Right. Let's try the next one. Right, guys. Okay. It's the population of both species. Okay. So it's there and it's there. I said about 1,500, 1,600. What did you guys write? Okay, so either or. The lemmings. Yeah, let's put it here. Lemmings is 1,500 about. Stoats is about 9, eh? Okay. Right, highlight on your graph. Okay. Where the lemming population is decreasing and the stoat population is increasing. So if you want the quadrants to help you, I don't know if it'll help us in this case. The quadrants get divided around equilibrium. But it's not always accurate. Okay, and they want to know, and in fact, it's not accurate all the time. Yeah, sometimes it is, sometimes it is, this time it isn't. Okay, so we want lemming to be decreasing, so we must be going towards the left, but the other one must be increasing, right? So there are two regions. Okay, well, the one is over here in red, right? That's your one region, where the one's increasing and the other's decreasing. There's another little region as well, though. This is like from there to there. You with me? Yep. Okay, now let's change the equation quickly. Okay. Everyone happy up to there? Okay, and they tell us that the equilibrium model changes to Stoke population is equal to Sn plus 0, comma, how many zeros? 4 zeros. 6 ln Sn minus 0.1 Sn. Okay. Right, determine the new set point of the two populations. That's nice, just the end of it. Okay,
No.
right, off you go. Okay, don't go learn formulas of powers. That's promise.
Be rational. Get real.
This is what I haven't seen. This is my preferred.
Jodie said, look at that, and I was like, no, like I said that's Miss Abdi, so it looks like something she would say. Oh,
Here's what I'm from.
saying yes.
First name is Robert again. Drinking coffee. Fishing. It's just like my mum.
So comfortably sipping his coffee.
Okay,
Yeah.
so guys, what's the key idea here of equilibrium? At equilibrium, what happens? What happens? The key idea is what? Sn plus 1 is equal to? That's all, okay? So let's go check this. Okay. Remember, we use a predator formula to get prey equilibrium. So we're going to actually find the equilibrium of lemmings here with this new equation. Okay, so go try isolate that in.
Sorry, man.
Okay, isolate ln. So you're going to have, first of all, Sn plus 1 is Sn, sorry. So those will cancel. I'm going to move that to the other side. You happy up to that? Can I divide both sides now? Fine. Get rid of the Sns, right? Tell me what you got, okay? Everything is. Okay, it's a 5,000 over 3, basically 1,667 approximately, yeah? Again. Doesn't matter. I mean, you're not going to get half a decimal of 11. Okay, so these are always just approximations. There's no way they're going to be exactly 1,667. Right, so that's the equilibrium point of the lemmings. I mean, of the lemmings. Now we need the equilibrium point of the stoats, right? So now, to get equilibrium of the stoats, I have to use the other formula. So to get equilibrium of Sn, you're going to use the ln formula. Yeah, so go write down your ln formula. That hasn't changed, just the stoat one has changed. So your lemming formula is ln plus 1 is equal to ln plus 0.8 ln 1 minus ln over 10,000. What's it? Minus 0.02. Right, so there's my formula, right? Okay, so first of all, what's your key idea with equilibrium? Yeah, good. Nice. A lot of tea today, apparently. Been a dramatic day for Pierre. So much tea today.
So Friday, oh my goodness.
Body. Body, whatever.
Yeah.
Really get out of
Well,
there.
and sorry, Emerson posted back. I think I know I was there. And yeah,
You recorded it, punch your names.
oh no, well, it was just, well,
She was gonna share them.
Were you shocked?
I was like quite shocked. There was like not many already people there. But like, yeah, no, it was most like the A levels because I went with my friend at A levels, like invited me, but. No, it was quite well. Like I was a bit shocked. Like I don't think. Like it was like seeing your Instagram feed in like a real life. It's just like.
Okay, so those disappear. It is a good one. Right, okay. But now, at equilibrium, what's ln equal to? We've worked out. Is 167, right? So the ln's cancel, right? We're looking for equilibrium of the stones. Okay. So Sn is going to be equal to 0.8, 1 minus 1,667 over 10,000, all divided by 0.02. Yes, we start with the predator model in order to get the prey equilibrium. Okay, so we started with the Stokes model, and then we got the Deming equilibrium. Right, so you're going to always start with the Fox formula and get the rabbit equilibrium. Then you're going to work with the rabbit formula and get the Fox equilibrium. Okay. You may come through, madam. How are you? Good. Okay, and what did you guys get for that? 33 about. Yeah. So Sn is equal to 33,33. Okay.
So aren't you supposed to say 30?
So it's approximately 33. Okay. All right, awesome. We ran out of time. This is a short. Okay, I want to just go back a page to the other model.
To start with this, would it be the same as when we do between 33 and 34?
Yeah, same kind of thing. That's the best way of writing it. Okay. Right, now we're going into the different model, right? The logistic model. Okay, I know you did the kind of thought a little bit. Okay, in 1888, when the Kruger National Park, page 33, was proclaimed the game reserve, the elephant population had been hunted close to extinction. In 1905, 10 elephants were recorded in the park, but since then, conservation efforts have ensured the growth of the elephant population. From the late 1960s until 1990s, culling operations were used to control the elephant population because the park managers decided that 7,500, stay with me, elephants was the carrying capacity of the park. I know you did. The intrinsic annual growth rate of elephant population is 0.15. Use a logistic model to answer the following questions. How many elephants were in the park in 1920?
Why did they give such irrelevant information?
I don't know.
Always, modeling is always like that.
Okay.
You know, when we do about Tuesday, and we just go on and on.
Okay. So, first of all, logistic model. Go to your formula sheet. Tell me the formula. Tn plus 1 is equal to Pn plus R in 1 minus. Right, so we're going to be using that formula. Okay. I want to know how many were in the park in 1920. Okay. This is for question 4.1. Right, what did they tell us? And they told us in 1905 there were 10 elephants. Okay, we want to know how many there are going to be in 1920, right? Do we know R? Intrinsic, what's R equal to? 0.15. And do we know K? Which, by the way, it proved to be, well, let's debate it. Yeah. Elephant numbers include go now sitting at about 35,000. Okay. So K is 7,500. That's what they were working. Okay. Question was, how many are going to be in 1920? Okay. So what's my formula going to become? Pn plus 1. Remember, this is recursive. Is equal to Pn plus 0.15 Pn. 1 minus Pn over 7,500, right? So how are we going to work out how many there were in 1920? Okay, we're going to remember put in our initial population. What's our initial population? We're going to call this P0. And what are we trying to find? Sorry, this is P0. 1920, how many years after that? We're looking for P from 1905 to 1920. 50. So we're looking for P50. Okay. Okay. Right. So what we're going to do in our calculator? What's our first number going to be? What was the initial starting population? 10. So in your calculator, you're going to go 10 equals.
So you'll say like P50 is what you're
You're looking for P15. Yeah?
50.
You're going to go 10. On your calculator, you go 10 equals. P0 population was not as P0. Okay. So P0 is 10 elephant, right? So you're going to go 10 on your calculator. 10 equals, clear your screen. Okay. Right. Okay. And then you're going to go what? Every time you see Pn, you're going to press your answer button. Okay. So you're going to go answer. Okay. Answer plus 0.15. Answer 1 minus answer the 7,500. And then press the button 15 times. I got 80.7, so between 80 and 81. Okay, so P15 is equal to 80.7 between 80. That's the proper way you're really supposed to write. Somewhere either 80 or 81 elephant park in there. Fish? Right, now we're going to use this graph. Okay. Okay, below the graph showing the relationship between the growth rate, the logistic growth rate, remember, is delta P over P, okay, and the population P. Now remember, your population logistic growth rate. Okay, the important thing to remember about this diagram was what? What is this value over here? The maximum logistic growth rate is the intrinsic growth rate. So this value over here is R. Okay, remember that? What's the maximum population in the logistic model? It's the carrying capacity. Remember that this model is EVPR. Okay, so R is the intrinsic growth rate. Okay, K is the carrying capacity. Okay. But give the exact values of the X and Y intercept and say what they represent. Well, let's answer that question really. Okay, so the y-intercept, x-intercept is what? Well, they told us what the carrying capacity was. So it's carrying capacity, and what did they say it was? 7,500. So this thing over here is 7,500. You have to give me 3 minutes to about this. And we've done at least a couple of each model. Okay, right. is 2 minutes. Okay, what's this thing over here? Value R. Yeah. What was the intrinsic growth rate? So the y-intercept is intrinsic growth rate. What's it? 0.15. So that is 0.15. Right, the next one is just y is equal to mx plus c, right? So in this diagram over here, now they said go find the equation of that relationship. That's 4.3. Okay. Right, you're going to use y is equal to mx plus c. Your gradient is what? Change of y over change of x. What's your change of y? If you're moving from here to here, how much have you moved down? Negative 0.15, right? The change of y is negative 0.15. What's your change of x? 7,500. Okay, and if you work that out, you should get negative 0.402. Okay, and do we know C? What's C? 0.15, right? So in terms of y, it's y is equal to negative 0.0002x plus 0.15, because C is 0.15. There's your y-intercept over there. But you can't do any of these questions if you don't recognize that your y-intercept is your intrinsic growth rate, your x-intercept is your character value. But we're going to leave it in the right notation. What's your y value? It's a logistic growth rate, 1 second, which is delta P over P. Okay, so delta P over P is going to be equal to negative 0.0002x plus 0.15. Not x, it should be P. Nearly done. Right. Right, so off you go. Next question. Okay, now we're going to just use that formula. And it says for 4.4. What is the growth rate? In other words, what is delta P over P when the population was 3,000? What are we simply going to do? You just connect, no, you just going to sub in 3,000 into that formula. Okay. As P, yeah. The P is equal to 3,000. So therefore, delta P over P is equal to negative 0.0002 times 3,000. I'll tell you the answer, don't worry about your calculator, and you should get 0.09. Yeah. Okay. Right. And last question. Yes. Well, let's have a look. So at 3,000, which is almost 0.1. Yeah, it doesn't quite. Doesn't matter. Okay, the graph's probably not to scale. Okay. Right, and last one. Okay. Now that's all. It's just the other way around. Okay, in B, delta P over P is 0.05. So you're going to get 0.05 is equal to negative 0.0002 times P plus 0.15. And if you solve for P, you're going to get P is equal to 5,000. So 5,000 elephants goes with the growth rate today. Right, well done, guys. Okay, so the revision consolidation. Quite enough questions. We will do revision lessons. Okay, so the 2 revision lessons. The first one is just paper 1. Okay, and then the core paper 1. Honestly, for you guys, I don't know if you need to be at the core paper 1. I think honestly for you guys, for core paper 1, I would just rather work by yourselves. So AP paper 1, you might want to come. Yeah. All in that time table. Yes. Up to you. Sometimes it's easier nowadays to, you know how you work best. Yeah.
You know what that guy in the beginning?
Yeah. Yeah.
Mr. Simpson taught him.
Really?
Yes. How funny.
Yeah. All right, thanks, guys. Nearly there. It's never been compulsory. No, well, I'd suggest you try it. Okay. I mean, it's not going to go into any term mark. Okay. It's the point of that test was to improve the paper two. Paper two too.
Stats and who knows how long.
Well, that's all right. It's fine.
I think I'm just gonna do like a worksheet.
There's like a word, you never know, you might surprise yourself. And we are the two easiest topics in paper two. Okay, with the other tests that you have in paper two, were your June exam, paper two, which was faster. Okay, and then you have the one other paper two test. So the whole point is, trust me, I have to set the test, I have to mark the test, doesn't mean anything. Okay. Well.
What's this reality to not I'm gonna be here tomorrow.
You want a better paper to do, I think.
Well, don't feel sorry for yourself then if your paper two marks not what you want. All right. No worries.